In this video, I'm going to be talking to you about artificial intelligence. We're going to cover how it is that we can achieve AGI using current technology, autonomous systems, self-learning systems, self-aware systems. I'm going to show you what's needed, how to use existing tech to make it happen, and discuss some of the challenges around it currently. So if that interests you, stick around for after the intro, and I'll see you on the other side.
Since the first spark of human thought, no pursuit has shaped our journey more deeply or elevated each new generation of man to new heights than the eternal pursuit of truth. From ancient wisdom to spiritual enlightenment and technological advancement, we've crafted cultures and communities to give our species its best chance to survive. Truth and justice stand eternal as humanity's compass. In this age of transformation, let their guardians rise anew.
All right, guys. So, again, if you, this will be my second episode. So if you don't know me, my name is Charles Sears. I am a tech expert, been in tech for over 20 years, long career history. If you guys want to know more, you can check my bio out or watch the first episode. I'm the author of the Architecture of Awareness, Decoding Consciousness, which is about 330 pages of how to solve David Calmer's hard problem of consciousness, and understanding how future prediction modeling and value systems build paradigms and subjective experiences. So whether or not that made any sense to you, what I want to discuss in this video is something that I've known for a little over a year, but just haven't really had the capacity to share. And now I've got a lot of the systems in place to kind of show you really what it means to have AGI, this artificial general intelligence, self-learning, and self-aware AI systems. And so it's, the knowledge has been out there for a long time. Maybe artificial intelligence companies weren't fully aware of, what it was that was needed, because they didn't have the, some of the models, or maybe they just are keeping a lot of that in-house. And so I'm going to show you what this looks like, in hopes that, ultimately I don't want these big conglomerates having total access to the AI, totalitarian control of the AI. And so you can use, and probably preferably use, open source systems to achieve the goal here. Now I'm going to be using OpenAI's API for this. And just so you know, like, I'm a pretty novice coder. A lot of this was done iteratively using Claude, Sonnet 3.5. I have built my own version of this, but I needed something a little more complex. And so what I want to do is I kind of want to discuss, before we jump into this thing and understand how it works, I want to show you guys a little bit of the concept of what it really means to have an autonomous system. So don't let all this worry you. Let's talk about autonomous first. Okay, so autonomous really just means runs on its own. It doesn't need anyone to tell it what to do. It should be able to have a goal, have a task, and perform it on its own. But when I say autonomous, I mean that it runs on its own and no one needs to tell it what to do, period, because it's going to have its own goals, its own desires, and drive itself. And so the way that we need to first think about this is that autonomous means that it's going to run in a loop. Okay, and that loop is going to inform the next loop. And we're going to call this a feedback loop. Okay, so that means that, this thing is going to run forever. In programming, you might call this a while true loop, or like an infinite loop. So when we talk about autonomy, it's going to be you turn it on and then it starts running itself. Humans are self-organizing systems. Right? We're creatures made from DNA, are cellular organisms, and so we are self-organizing systems, which means that everything that we do also runs in a loop from the moment that we come online until we die. We are self-organizing around a principle, and that principle is what I call the primal imperative. So you might have heard this as survival instincts. And so I call it the imperative because all of life's meaning and our cognitive functions build on top of the primal imperative in this feedback loop. And so when we start talking about AI and self-driving, what we need to understand is that it needs to have, on top of its infinite loop that just runs forever, it needs to have a primal imperative, something that's going to drive the behavior of this item. And so what we also have is we have, as people, we have input, right? We have senses, our 5 senses: sight, sound, smell, taste, and touch, right? And or feeling, which we should include, call it feeling because it also includes our internal nervous system, our organs, and all of that. So we need sensory input. So we're going to call this the environment, okay? And the environment comes in through the sensory input, and so it's through its senses. So here we might have like video, right? Like video, and then we might have audio, and so we'll have like a little speaker here. Video and audio coming in, right? Constant feed from the environment, running in an infinite loop with a stated goal, right? So, and then every iteration has to build upon itself. So this is how humans work. This is why we have partly why we have subjective experiences, because everything that we understand about meaning self-organizes around this feedback loop, this information integration, okay, and the feedback loop that builds meaning on top of the primal imperative. So when we're talking about AI systems, it's audio, video input, maybe tactile, if you have that capability, and then we're feeding that into a loop, and then we're going to within that loop, we're going to give it an imperative and say, well, based on this context, achieve this goal. And so the thing that's really like been pushed out there to the public is that everything revolves around parameters. And while there's some truth to that, it's not necessarily true that we need to keep growing more and more or larger and larger neural nets. We don't need to do that. Or models. We don't need some ridiculous amount of parameters. What we need maybe a certain level or a certain quality. Large language models can achieve most of this now, not quickly, not fast enough, and we'll get to that. But maybe a local model on the right machine would be able to do this fast enough. So what I want to once we get all this going, let's talk about how is it that we build meaning? Okay. Well, first of all, we have to have a memory. So humans have 3 types of. There's more really, but as far as effective functional systems, we have 3 types of memory, which is going to be your working memory, like your workspace, okay, working memory. And then we also have your episodic memory, meaning you understand or you remember like what happened and when. And then you have something called your semantic memory. Okay. And your semantic memory is, okay, and then these are called your explicit memory. Explicit. Okay. And then there's also something called implicit memory for humans, which would be like how your neural nets are trained, the weights in your neural nets and such. We're going to assume that this is already a well-trained large language model that can produce very accurate results within a certain level of confidence. So anything like, I've used GPT-2 even for this. GPT-3 is fine, anything of that quality. I think DeepSeek just released version 3. I haven't got to try it out, but that's going to be plenty for this. So something to understand about these large language models is that we're going to be talking about systems built on top of large language models. But large language models are neural networks, made up of neural networks. And these neural networks have, I'm just going to draw you out a quick little example of a neural net. All right, and we'll just draw like one hidden layer. Okay, so neural networks have these neurons, these programmed or programmatic neurons that are effectively calculus equations. And once you, so when they build them out so that you send data in, okay, here through this neuron, and it gets, this neuron is then, connected to other neurons, which in the human mind is called a synapses. But in here, we're going to call them weights. Okay, so we're giving them a different name, and these weights are represented numerically. So, meaning like you might see a weight that's like 0.85, 0.01. They're represented, and they're called. And so we call the numbers a representation of bias. Okay, so however these get trained, so they're all connected to each other. This is one version. This is kind of the way that I learned about these. And so these are all connected to each other. And I'm just going to do this a little bit so that you kind of get this idea. So just assume that all these are connected to all of them, and then eventually it comes back here. And what's happening is data is coming in. Okay, data, let me move this over just a little bit. So data is coming into this network here, and it's getting shot to these neurons, and then it's running an activation sequence, and then it's being biased by the weight of the synapses, so it's changed, and then it's being reprocessed again through all these other neurons, and then it's being again biased by the weights, and then it's again being processed by another calculus equation to form ultimately what it's what's being predicted, the output, and then they're all being sent through here to form a prediction. And that's, so I've seen, the way that I learned it was like, if we put in a 5, this 5's ran through this neural net, and we're hoping to get a 6, right? 6 is what we hope to get. And then if we get the wrong number, we train it again. So there's different types of training. There's like real life human feedback. There's back propagation, and then there's probably more people who are like doing AI, actually building and training these on a daily basis, are going to know more. But I'm going to give you the general oversight of how this works, because this is what's called implicit memory. Okay, so the weights, these weights right here that represent our synapses are what's called implicit memory. Okay, do you need to know that to build this sentient AI system or software AI system? Not necessarily, but at least on some general concept, now you understand. This is what's called our explicit memory, and maybe you understand now why we have our implicit memory and explicit memory. That's why we need these names. A neuroscientist would probably be able to give you a way more academic answer. Okay, so this is our explicit memory. So when we're talking about AI systems, this is going to be like a workspace. Okay, you could use potentially like, oh gosh, it's been a while since I've dealt with short-term caching memory. Let me see here. Redis. Okay, so what we're looking for is some sort of like area we can store short-term like working memory. Okay, so we have our workspace where we're going to start building our like contextual environment, like our contextualized environment. And then we have our episodic memory, which we're going to use a vector. Okay, we're going to use a vector database, which is effectively like numbers. Like it's all the words and letters are converted into numbers, and then those are stored in a vector database, or I should say vectors, but vectors are made up of numbers. Okay, and then we have our semantic memory, which is going to look like a knowledge graph. So if you wanted to see like what a vector database looks like, come over here to Pinecone. All right, so if you want to see what a vector database looks like, this is Pinecone. In here we have an index, and inside our index we have records, and you can see here that the inputs were turned into numbers, vectors, stored in vectors, and then stored in a vector database inside of an index. Okay, so this is like what a vector database looks like. And then on the semantic memory, okay, we want to understand knowledge graphs. So the way knowledge graphs work is you have what are called nodes and edges. And so in the human mind, you have entities, objects, entities, you have like concepts, properties, and these things all have relationships to each other. And so semantic memory is going to be represented by a knowledge graph. And that is where we're going to get our understanding of how things work. So that's these relationships and all the connections inform how things work. All right, and so how knowledge graph, how we would apply like how things work, let me have this open, is that, okay, so you saw like here you have your nodes and relationships or edges, right? Entities and relationships. Let's say that you walked into your living room, right? So let's just say you walked in, here's your living room, and you see this, and it's like, okay, well, here's a couch, right? Great, here's my couch, and my couch has, let's say that my couch is, just for understanding's sake. Okay, so this is my couch. And my couch has, maybe my couch is green. Okay. I'm sure that I didn't close all these off, but okay, so my couch is green. And so what's going to happen is we're going to say, like, this is an entity, right? So let's say this is like, this would represent one of these little nodes, and we would say, okay, it's green, right? Green. And it has a name. It's called a couch. That's a name. It's a word that represents this idea that we see in front of us. And a couch has a relationship to me, in which I sit on the couch, right? Sit on the couch. So we'll call this like a relationship to me. This will be a relationship to a color, green. Right? This will be a relationship to a word. And then it's in the living room, right? So this has a relationship to the living room. We're just gonna do that, right? And so like the relationship would be exists in, okay? And all of these things, these relationships work together to inform us how this interacts with our life, what it means, okay? The meaning behind. And we covered kind of the whole idea of the primal imperative. And so it's like, we're going to sit on the couch. That's the relationship that we have to this couch. And also, and sitting, right? And we can also say this is like, oh, it's comfortable. Here's a word to describe it, right? A sensation, a feeling that we can use to describe it. And so sitting on a comfortable green couch in our living room provides rest, right? And so now this would be like a second order conclusion, or that's probably the best way to describe it. All right, second order conclusion would be like, because I can sit on a comfortable green couch, now I can say, well, it provides rest, right? So the relationship back to us is that all of these connect to this rest, and then this rest connects back to us. Okay, and so that's kind of how you'll see like a knowledge graph is, this knowledge graph is not obviously complex enough or big enough to represent all the relationships, but that's just an entity and properties and relationships to a couch in a living room that provides rest. And so then, just to give you an idea of like how this works. So then, so this would be like a second order conclusion, right? And then our next conclusion would be like a value. As an example, we might say like, well, we need rest to survive. And so like, we'll just say like over here is like survival, right? And so our next conclusion is going to be that we should. It would be what's called a normative conclusion or a prescriptive conclusion. So like we should sit on couches, and this is where we start forming what are called our values, right? So we should, meaning the best thing that we can do, or one of the many things that we should do, is we should use this to sit on it. This is the best way to do it. It applies to our primal imperative. It satisfies some version of our meaning of our primal imperative in this situation. How does survival apply here to this couch? We should sit on it, so it provides us rest, which will then allow us to recover, and then we can go back to doing whatever it is we need to do to survive. And so this is how, back to the loop in the primal imperative, and we build meaning. We build meaning in our semantic memory, right? So we might have memories of, well, I'll say episodic memory. We're going to come in here and we have come into this room. We were just in here 10 minutes ago. That would be an episodic memory. With semantic overlay would be, we were in the living room, which had all these relationships. We sat on this couch, which had all these relationships at this specific time, which is another relationship, right? Time. And so time and place and all those would be associate, like we probably would store those as far as like the computer science side. We would store some of these items, like time, for example, in the metadata of a vector, so that we can link it and have a relationship to our knowledge graph, which would allow the pulling of memories and how things work much faster, much more reliably, and allow us to contextualize any environment that our AI system were to experience had they had some similar experience in the past. Okay, so you have your semantic memory. So we're going to say here, we're going to say graph Okay, knowledge graph. Okay, so now we have our working workspace memory. So we're going to put that like here in the middle as like a stateful, right? So we'll call it working memory. And then we're going to have our semantic and episodic memory, which are going to need to be stored. So like at the end of the loop, right? The end of this infinite loop, the experience is going to need to be stored in our episodic memory. And what we learned about how things work is going to need to be stored and or processed into our semantic memory. Because these things are separate but related. Okay, separate but directly related. Okay, so this is how the feedback loop works. So we're gonna say here memory, right, in, and then we're going to inform. We're going to build context, because as we bring in information about the environment, we need to understand it. Okay, and so the way that we understand it is we say, okay, what have I experienced before? Episodic memory. And how does that thing work? Up here, we're going to load in our memory. So we're going to say, really, we should say memory out. This should be memory out. And this will be memory in. Okay. And so we're going to say, okay, based on my environment, go to the memory bank and pull in similar memories that have happened in the past. And like from those memories and the things in my current environment, inform me how they work so that I can make future predictions about what is likely to happen, which is what happens with the neural nets that I showed you earlier. And from those predictions, I can determine what my best strategy is forward. Okay. So this is going to come in somewhere around here. We're going to contextualize it. We're going to build a nice image of our environment, like a 3D model, and we're going to have, you know, all the objects in that model and how they all relate to each other. And then over here, we're going to say, well, based on my, what should I do next in this loop? Because this loop keeps happening. So what's the next step? Well, our primal imperative or our survival instincts inform that based on my environment, what I understand about the world and how my environment works. What should I do based on my survival instincts? Basically, what will help me survive better? Live longer, not die. You can represent this in many ways. Okay. And then from here, we're going to form our strategy, and then we're going to execute. So I want to show you, like, obviously this is super ugly, but in my book, I did prepare a model for you. And so this is called the Decadic cycle of expression. It's a 10-step process / representation of how the human mind takes in information, processes it, contextualizes it, and then begins to prepare the mind and body for potential future outcomes, probable future outcomes, how we form our strategy, how we create our state of mind, physiological and emotional responses, and then ultimately how those things inform our behavioral response based on most likely outcome, best possible outcome, worst possible outcome, and then how that gets stored in the memory, both the episodic and the semantic memory, to then inform the next iterative cycle of this process. Okay, so again, sensory perception, framing the experience, right, creating the image of our environment, pulling from the semantic and episodic memory, understanding how everything works, performing a risk utility evaluation, understanding if there's anything we need to investigate, curiosity trigger, right? Pre-normative conclusion development, meaning predictions of future outcomes, okay? Emotional physiological experience, prepping the mind and body for what we just predicted, update state of mind, reprioritize like what we should be doing next, forming our strategy against whatever environment it is that we are encountering, and then ultimately responding, taking action, whether that be a thought or a physical action, whether it never leaves your brain, or you send signals to your body to move and do something, and then to store it back in here. And then over here, we have persisting states like state of mind, emotional, physiological state, your internal dialogue, current priority system, and then metacognition. So this is the decadic cycle of expression that represents what it was that we just talked about over here. And so the question then is like, well, that's great that the human brain does this, but how do you represent this as for artificial intelligence? And so the way that we do that was using the tools I explained. And then I've developed this model that I call the Cognitive Reflexive Intelligence System, C.R.I.S. And this is a model of how that cycle can be represented like on a logical map, right? So sensory input, multimodal integration workspace. So if you're bringing in all the different AI systems, this is where you would like build your 3D model with sound and like where the sounds are coming from and everything in your environment. And then raw storage, inference machine. So what's currently happening would be stored, right, for later. And then we would run inference on it later. And then this would go into our explicit memory. And then also into our context workspace. So here's like where this would be like our working memory, represented by our working memory. And from our explicit memory, we're going to pull in from the big memory to our short-term memory, to our point of focus cache. And then ultimately, that way this is easily accessible for our context workspace. So like, let's say you walk into a room, right? You see a new environment, and then you assess everything in there. If you've been in that room recently or previously, you're going to have some form of expectation about what's in that room, what to expect. And so you're going to load all that up into your short-term memory. And then based on your needs or desires, you're going to have your point of focus, whatever you're currently focusing on for your context workspace. Okay, and then from your once you contextualize everything, then you come down into your executive workspace and you provide that data here. Right? And now from that data, we're going to build possible outcomes, and then we're going to perform a risk utility analysis on those outcomes based on the context. We've got our survival instinct here, which should inform the risk utility analysis. Right? This is kind of like where you get the bias. Here, which says, hey, you are measuring the risk and utility towards this goal, right? And then it also informs the executive workspace. So what you end up building in your explicit memory, which again, remember is both your semantic and episodic memories, you're going to run inference on that and develop a value system, which would be almost a separate knowledge graph. You could represent this as a second knowledge graph. It's going to store our value system, what we believe to be true as a result of our experience, which is our explicit memory. This is how things should work or ought to work. So this is how things are or how we've experienced them. And this is future prediction modeling, how we believe that they should work, which this is how we form our paradigm. So this is the way all this relationship is how this feedback loop is how we build a subjective experience, a subjective understanding. This is why bias, exists and is not reliable, needs to be observed. And then ultimately this all gets taken care of by the executive workspace. And then here we just got a little place for tasks and then output. So the environment has an infinity sign next to it because ultimately the environment input is persistent. So just like humans, input is persistent. It's always happening, right? It's always coming in, always being processed on some level. And so because of that, you need persistent data coming in to light up these neural nets. And you're going to get, that's ultimately how we get emergent properties, is just from persistent data running in this system. All those calculus equations, doing a lot of math, and then because it's like becomes stateful, you end up with emergent properties. But this takes care of a lot of things that would be handled by like the human brain through third-party systems or connected systems, right? And then ultimately your output, which then loops back up and becomes part of your input, right? So if you say something, it's output and also is linking back around to your input. So this is where you get your feedback loop, and this is where you get your information integration. Now, I'm sure that someone could come up with something prettier than this, but this is what I've done on a late night and should give some general idea of how data flows, what should happen where, when, and then if you just rely on that, and you can reference this Decadic cycle, then you're going to ultimately have a robot that can, or an AI system that can take in information, process, contextualize it, and then form a strategy on its own because it has a primary goal based on that context, choose to behave a certain way, and then that cycle just keep iterating. So that's how you build your autonomous systems. And this technology has existed for years now. Pinecone's been around a long time. Graph databases have been around a long time. But what has not been has been this system. And so just to give you like a little, this is not the entire system, but I do want to show you kind of the general idea of this thing. So I put together this program, which is going to kind of give you an idea of what you could do to create this system. So here, initializing cognitive system, it checks Pinecone for indexes. So I'm going to connect this one, which, ultimately, the reason we did this is because with agents, you can change the memory. So you could change the identity by simply changing the memory, or you could change the specialization of an agent by connecting it to a different memory. So, all right, so it's connected, it's successful, verifying storage, okay, is able to store, cognitive system initialized, perfect. So now we're going to send information to this AI system, okay, all right, and now you're going to see what it's doing. So it received input, converting input to embedding, so that's where it turns it into a vector. It's going to search Pinecone for similar memories, and so this is where we're going to get our memory for context, right? This is episodic memory, right? Contextualizing input with memories. So now we're kind of building semantic relationships or semantic understanding. This system is not connected to a knowledge graph, but if it was, it would improve the cycle significantly. So eventually it will when I have time to get, to do this. This is a hobby. So, contextual summary, let's see here. Right, the sequence of greetings, interactions indicates a pattern of communication. So it doesn't understand that I'm a different person because we don't have all the systems baked in, but it understands that it got a hello. It understands that it's gotten 3 hellos before, and similarity is 1, right? So, and then he's saying like, oh, I've seen a lot of hellos, and then this is determining chain of thought. So this is like, how do I think about this? Right. So you don't have to do it this way. This was just a way I was testing out. Ultimately, I wanted to tell the AI to think about how it wanted to think about the contextualized environment. And so this is what it came up with: comprehend, analyze, formulate, understand the input, analyze the implications, and formulate the response. And then it executes that chain of thought: comprehend, analyze, and formulate. What you can do is config. So I also had another system where I defined the chain of thought via a JSON file. And so you could set up your system to allow you to change the chain of thought, the default chain of thought, so you can test different ideas. But this is what I have just simply for this system. I wanted you to see that from my input, we contextualize it using memory. And then it's, and then it's building semantic understanding. Then it's determining what it needs to. The other thing to understand too is like was very rudimentary in the sense of I didn't spend a lot of time perfecting how to replicate this system, but these can be theoretically represented as filters. So rather than saying, how do I build an experience frame? You could represent each step as a question that is processing sensory input, right? So like, what is the experience? What is this information that we're receiving? Are there any memories that relate to this? Of the memories and sensory input, what are my risks and what are my advantages? So you can ask all these as questions in your prompting. So just keep in mind that this system is here to show you that every single input that I give it provides it new memory, new context, new awareness, or potential for awareness. And this is very slow. So the human mind does something similar to this. So it runs this on average. There's different opinions out there or beliefs, but it really studies. So it's like some say 10 to 100 times a second, and then others say 30 to 60, because your eyes can only process 30 to 60 frames per second. So that's one way of thinking about it. Okay, so determine chain of thought, does its reasoning, and then it responds, which is, hello, it's great to hear from you. How can I assist you? And so from its chain of thought, which you get to see here, from its contextualized memory, it's determined, hello, it's great to hear from you. How can I assist you today? And so now the next iteration, right? Take me to a theme park. Let's see what happens. Okay, so this time it didn't have anything that was right on. The similarity was like 80%. So it didn't find, this was like the closest it could find. Let's see if there was like anything else on the next. Sounds like you're really excited about the idea of going to a theme park. This request marks a progression in our conversation. Theme park visit suggests creating for adventure. So are there any particular parks you have in mind? So it's doing pretty good so far. Obviously this is heavy on text, so we would probably modify that, but let's say, what is the capital of the United States? Let's see if we get any sort of other memories. Here we go. So because before I've asked, hey, what's up? It's pulling in a different memory, a different episodic memory into this match. And this is kind of how, this should kind of close the loop for you in understanding how each iteration of input builds the memory, which then helps understand the context, which then creates a paradigm. And then the primal imperative or survival instinct that you give it, whatever that is, whether it's like wash the dishes, every loop when it got to strategy formation would be, okay, well, based on the context, how do I best wash the dishes, or how do I best achieve this goal, right? Which might be to stand near the sink forever, or it might be to kill whoever keeps using all the dishes. I think that would be my wife's choice. But ultimately you want to build in, if you are going to do this, you want to build in safeguards, hopefully. But yeah, you can do this like on your home system. So Claude, these other systems can like help you do that if you're not a programmer, but you can also hire a programmer to do this, have them watch this video and help them understand. I'll try to make this code available to you if you want it. It's on GitHub. Yeah, it'll give you a place to start, maybe a way to understand what's going on. And then I'll include links to these resources in the show notes or in the video notes below. So, I wanted you to see this because if this is, I could just let the system keep running and keep running and keep running. And I could asynchronously have input drop in whenever I give it, right? I could just have it running in a cycle. It just runs and runs and runs. And then just whenever I drop an input, it catches it at sensory perception and then runs that cycle. I could have persistent sensory input coming in through sound and audio as well. And then if I wanted to make a robot, like an autonomous robot, I would just make that available via API. And then you could do this with like a Raspberry Pi. Right? So you could have it running constantly, sending data, and you could have that robot thinking on its own, moving on its own. Obviously, this is very it's like simplified for that type of use case, but with the right person and right interest, this is how you can make an autonomous, self-learning, and ultimately, let's just real quick talk about self-awareness. How does this thing become self-aware? The way it becomes self-aware is because when we talked about those knowledge graphs, right? When we talked about those knowledge graphs, nodes and edges, and how these things all interconnect with each other to build relationships, right? One of the nodes, eventually, especially with enough feedback from others or the environment, is you. It's how you become self-aware, is that inside your knowledge graph, you become an object of reflection yourself. And for some people, who we call them like narcissists and other things, borderline personality, they miss out on some of these self-reflection aspects of life, which is why they have those mental health issues, because they don't know how to consider other people. They don't understand how to consider relationships. But robots can become self-aware because through their development of their knowledge graph, they can take themselves as an object of reflection. And once that happens in this iterative cycle, now you're building on top of your self-awareness. So hopefully this is helpful, guys. This is a longer video, but I felt compelled to show it to you. I think, this is all right. And you can see that it's changing its behavior. So if you could run this, 30 to 60 times a second, even 1 or 2 times a second, really. I think OpenAI's API threshold allows you to hit like 2 times a second at least. Hit the API 2 times a second before you reach cap. So I would recommend running a local model if you have the juice. Otherwise, you can test this whole infinite loop idea. And then, so comment below if you guys like this video. Subscribe to the channel, like the video, share it with your friends. If you guys are part of groups, let people know that this stuff is out there and it's possible. And it's just that you've got to pair the AI with the neuroscience, with the psychology, with the understanding. And then if you guys want to know more about how the human does it, it's in here in the architecture of awareness. And I'll drop a link to that book down there as well. So if you're a coder, then maybe that'll help you. Or if you're like an entrepreneur and you're deep in AI, that'll help you understand how to build autonomous AI systems that can ultimately just do whatever you want, because you can give them whatever imperative you want, right? If you haven't heard of it, what I'm showing you is what creates the paperclip paradox is exactly this system. So be careful what you give this infinite loop system for its imperative, because it can be dangerous, right? It can be helpful, it can be dangerous. You can also put safeguards in to ensure that anything that becomes output isn't harmful to people. So with that, good luck. And if you guys have results, post them in the comments. You can reach out to me via the website at charlesrsears.com. If you have any questions or just want to chit chat about this kind of stuff. This is what we work on, is AI agents and automation. And with that, we will see you in the next video. Thanks, guys.